Okay, I skipped over our little name that term game. It's fun in a classroom, not so fun in a video. So let's jump right into it, into the Zeroth Law of Thermodynamics. You'll be wondering, like, why in the world do they call it the Zeroth Law? Well, it's because it's pretty obvious, and since we already have a first and a second, we just decided since this is pretty obvious and it's kind of foundational to everything else, let's put it before those two, and so we have Zeroth Law. Kind of awkward to say, but it's really easy to describe. So what you see right here is we've got two bodies, iron and copper, and they are not in thermal equilibrium. You can see that one's 150 degrees Celsius, the other one is 20 degrees Celsius. What the Zeroth Law says is that if I have two bodies that are in thermal equilibrium, they will be in equilibrium with a third body, which is simply saying that if I'm in equilibrium with something and something else is in equilibrium with me, then those two things are also in equilibrium. An even easier way of saying it is that if something is in thermal equilibrium with each other, it will have the same temperature. So if I'm 98.6 and something else is 98.6, we're in thermal equilibrium with each other. Now, as a note, if you go around touching 98.6 degree things, you will overheat. There's reasons for that. But if we're talking about like physical objects that don't have, don't produce their own body heat, then yes, if they're the same temperature, they are in thermal equilibrium with each other, which means that there's no heat transfer. Like at this point, there's no net heat transfer. As a note, Q is how we determine heat transfer, is how we write it, going from one to the other. That doesn't happen when they're the same temperature. Before that point, though, there was heat transfer, and over time, it eventually goes to zero. So that's the Zeroth Law. So if temperature is important, we should probably talk about what temperature means. So first off, all temperature scales, are based off some easily reproducible state. That is not 100% true when we get to absolute temperature scales, but for the basic ones like Fahrenheit and Celsius, they're all focusing on the ice point and the steam point for water. Like that's how we're determining where they are on those scales. So the ice point is simply where ice and water are in equilibrium. If you go lower than this temperature, then you're going to freeze. If you go above it, you're going to melt. This happens at 0 degrees Celsius or 32 degrees Fahrenheit. Steam point, once again, this is the temperature where liquid water and water vapor are in equilibrium, which means I'm not changing and getting more vapor or more liquid unless I try to go past this point. If I try to increase the temperature beyond this point, then it will go all steam. If I go below that point, it will be all liquid. So here's the steam point. Above that, I am completely a vapor. Below that, I am completely liquid. At that, I am 50-50. Okay, 50% here. It's going back, it's going forth, it's constantly changing, and it's only determined by, I say 50%, but it's not changing. The amount I have of each is not changing unless I try to go beyond that point. Okay. So, Celsius is what we use for SI, Fahrenheit is what we use for the English system, and then finally we have something called an absolute temperature scale. This is a temperature scale that starts from absolute zero, and this is called Kelvin and Rankine. As a note, Kelvin goes with Celsius, Rankine goes with Fahrenheit. But what in the world is absolute zero, and why would I care about this? Well, let's talk about absolute zero, and then we'll figure out where we're going from there. So, if I were to take some ideal gases, the gases that follow that whole PV equals RT equation, and I were to plot their volume with decreasing temperature, or plot their pressure with decreasing temperature, what I would see is that their pressure decreases linearly as I decrease the temperature. And what I would notice is that for different gases, there is this one common point where they would all have zero pressure if I continue decreasing the temperature. And so this point right here, which is negative 203.15 Celsius, that is absolute zero. Now, why do we care about this? Well, the reason is because 0 degrees Fahrenheit is not equal to 0 degrees Celsius. However, 0 joules is equal to 0 foot-pounds. 0 inches is equal to 0 meters. 0 pascals is equal to 0 psi. All those other things are the case because they all are absolute scales. Energy, distance, time, mass, pressure, all of them are on absolute scales because they all start from the same point. It'd be like if you were running a race, okay? So you're getting ready to run the race, you're going fast, beautiful running thing here. But what you find out is because you're running it in feet, you're here, and your friend who's running it in meters, well, they get to start up here. Why in the world would that be the case? That doesn't make any sense. But that's how it is when we talk about temperature scales. 0 degrees Fahrenheit is much colder than 0 degrees Celsius. And so we developed this absolute scale so that we can convert between them rather than having to use a bunch of equations to do it. I could also look at various other ways of doing this too. If I go to an absolute vacuum, I would go down to negative 203.15 degrees Celsius, which happens to be 0 Kelvin. Okay, so here's another way we can look at this. So this is Kelvin on the right, Rankine on the right, Fahrenheit on the left, Celsius on the left, just to help us out here. What we see is that at 32 degrees Celsius, 32 degrees Fahrenheit, that is when water freezes. And for Celsius, that's 0. And if I go down here, at absolute 0, it's negative 273 Celsius and negative 460 Fahrenheit. So they have different numbers, which means I can't use a conversion, like I can't use my train tracks method to convert from Fahrenheit to Celsius. That won't work. I have to use equations. And as a note, relative temperature scales, which is what Celsius and Fahrenheit are, will destroy every equation we work with in this class. Okay, not always. If you have delta T, technically it's fine. But for the most case, you always absolute. That's why I tell my students, always absolute. So if you're given a temperature in Fahrenheit or Celsius, convert to Kelvin or Rankine. And here are some equations for that. Rankine, see, this is a simple conversion factor. 1 Rankine is equal to, 1.8 Rankine is equal to 1 Kelvin. The other ones, though, you're going to have to use equations to convert them. They don't have a direct conversion. Okay, we already talked about that. And so one last thing to show you is these are the relative size of different steps. Like 1 Kelvin and 1 Celsius are the same difference in temperature. They're the same step up in temperature. Just like 1 Rankine and 1 Fahrenheit are the same step up in temperature. And so when you're converting from one to the other, you still have to be careful about your how you're starting them off. But if you're just talking about changes in temperature, they're equivalent. I can show that to you. So if I have 100 degrees Celsius and I want to increase that to 110 degrees Celsius, well, I can also do that in Kelvin. To go from Celsius to Kelvin, I just add 273, so this is 373 Kelvin, going to 383 Kelvin. If I look at my change in temperature, that's just 10 degrees Celsius or 10 Kelvin. That is the same. Change in temperature is the same. Absolute temperature, the actual temperature, is going to be very different. So always absolute, you'll never go wrong with that. Make sure you do that and you'll have an easier time with your problems. Thank you so much, and next time we're going to try out an example, I believe. Yes. See you in a bit. Bye-bye.